tutorial, we will be discussing entropy. Entropy is a term coined by Rudolf Clausius in the 19th century. Clausius was convinced of the significance of the ratio of heat delivered and the temperature at which it was delivered, Q for heat over the T for temperature. Entropy can be thought of as a measure of randomness of a system. Think of it as if you have a dresser drawer and you clean it out over the weekend. And then throughout the week, it gets messier, messier, messier. We have a natural tendency to be more random. We have a natural tendency to be messier. That's what entropy is all about. It is related to the various modes of motion in molecules. One property common to spontaneous processes is that the energy of the final state is more dispersed, such as the dresser drawer at the end of the week. In a spontaneous process, energy goes from being more concentrated to being more dispersed. Entropy change, delta S, is favorable when the result is more random system. Therefore, it has to have a positive value for delta S of the system. There are several ways that this can happen. Molecular complexity. The larger the molecule, the more spatial the movements. Temperature, elevation, or energy flow. Hot flows to cold. Reactions whose products are in more random state, so it goes from a solid to a liquid to a gas. Reactions that have a greater number of product molecules than reactant molecules. Like the total energy and enthalpy, entropy is a state function, meaning that you can calculate it by doing the final entropy minus the initial entropy. For a process occurring at constant temperature, an isothermal process, the change in entropy is equal to the heat that would be transferred if the process were reversible divided by the temperature. This is the exact same equation that Clausius had given before. The second law of thermodynamics states that the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for reversible processes. So in other words, for a reversible process, the change in entropy will be zero. There will be no change. But irreversible will be greater than zero. It'll be a positive. These last truths mean that the result of all the spontaneous processes, the entropy of the universe increases. Ludwig Boltzmann described the concept of entropy on a molecular level. Temperature is measured at an average kinetic energy of the molecules in a sample, and that temperature, that energy, translate over to the differences in entropy. Molecules exhibit several types of motion. Translational, which is the movement of the entire molecule from one place to another. Vibrational, which are periodic motion of atoms within a molecule. And rotational. Rotation of the molecules about an axis, or rotation about a sigma bond. Boltzmann envisioned the motions of a sample of molecules at a particular instant of time. This would be akin to taking a snapshot of all the molecules. He referred to the sampling as a microstate of thermodynamic system. Each thermodynamic state has a specific number of microstates, W, associated with it. So therefore, entropy is K of the natural log of W, those microstates, where K is the Boltzmann constant, 1.38 times 10 to the negative 23 joules per Kelvin. The change in entropy for a process, then, is the change of entropy of the final minus the initial. If we combine these two equations, it's the microstates of the final divided by the microstates of the initial. Entropy increases with the number of microstates in the system. The number of microstates, and therefore the entropy, tends to increase with increases in temperature, volume, or the number of independently moving molecules. Entropy increases with the freedom of motion of the molecules. Therefore, the gas has more entropy than a liquid, which has more entropy than a solid, because of the fact that it has more room to move around and more directions it can move. Generally, when a solid is dissolved in a solvent, the entropy increases. For the same reason, the molecules are able to move around more. Also, in general, entropy increases when gases are formed from liquids and solids. Liquids or solutions are formed from solids. The number of gas molecules increase, or the number of moles increases. Probability suggests that spontaneous reactions or processes will result in a dispersal of energy, be more disorderly, and more places to occupy. As the size of a container increases, the number of microstates accessible to the system increases. Also, the density of the states increases. Entropy also increases at this time. When a substance change states, the number of macrostates it can have changes as well. The more degrees of freedom of particles have, the more macrostates are possible. Solids have fewer macrostates than liquids, which have fewer macrostates than gases. So let's break this down. Heating and airing the balloon, because you're getting it warmer and the molecules are moving around more, the entropy change is going to be positive. Water vapor condensing. The gas molecules are condensing down into a liquid. That's becoming more organized, so therefore entropy is decreasing. Separation of oil and vinegar in the salad dressing. It's once again becoming more organized, therefore the entropy is decreasing. Dissolving sugar in tea. The sugar is dispersing, it's becoming more disorganized. Remember, more disorganized is going to be positive. The more organized is going to be negative. Alright, so the next ones, we're actually looking at chemical reactions. What you're going to want to do is look at the differences in the moles. In the reactants here, we have 2 moles. And the products, we have 2 here and 1 here, for a total of 3. Therefore, we're increasing the entropy. The next one, we have 2 on the left. We have 1 for the nitrogen and 3 for the hydrogen, for a total of 4, which once again means that we're increasing. The next one, when we form silver chloride, we have 1 for the silver ion, 1 for the chlorine ion, making 2 on the left for the reactant and only 1 on the right. That's actually a negative entropy. So let's do this again. Letter A, we're going from gas to liquid. It's becoming more organized. We're condensing it down. Therefore, entropy is negative. Solid carbon dioxide sublimes, which means it's going from a solid to a gas, is becoming more disorganized. Therefore, it's going to be positive. N2O gas is going to gas. So we have no physical state changes here. Let's look at the number of moles. We have 2 on the left, and then we have 2 for the nitrogen, and then 1 for the oxygen, so we have 3 on the right. That's going to make it positive. Reactions are spontaneous in the direction of lower chemical potential energy. There are 2 factors that determine the thermodynamic favorability. One is enthalpy. In general, exothermic chemical reactions are spontaneous, but we'll be discussing this more in future tutorials. And then the other factor is entropy, what we've been discussing this entire time. Finally, the third law of thermodynamics. The absolute entropy of a substance is the amount of energy it has due to the dispersal of the energy through its particles. The third law states that for a perfect crystal at absolute zero, the absolute entropy is therefore 0. Therefore, every substance that is not a perfect crystal at absolute zero has some energy of entropy, from entropy. Therefore, the absolute entropy of substances is always positive. Once again, the entropy of a pure crystalline substance at absolute zero will be 0. And that is your explanation of entropy.